Hello everyone. This is a movie that kind of sums up what we've done this semester. So far, what we've really done is trying to answer the question, what is a mole? All right, so what is a mole? Well, in chemistry we need to be able to count things, and the things we are counting are extremely small. So we needed to develop a system that would enable us to count by weighing them instead of by actually counting the pieces. So the system we developed is really based on the gram formula weight of something. So I'm going to begin with that definition of a mole, quick little explanation of that, and we'll then move on to the other two definitions. So really there are how many definitions? Three. So three definitions. And I'm going to start with the gram formula weight definition. So if we had some kind of chemical compound, like suppose I said we have some nickel 3 sulfide. Now you remember that we've been working a lot on writing chemical formulas since December. So you'd look at the periodic table and you'd find nickel, it's Ni. And you'd find sulfide, which means just plain sulfur. Remember, if it ends in IDE, it's just plain sulfur. So you flip over to the periodic table, and nickel, you notice, can be either +2 or +3. You can see this little charges right here. You look at sulfur, and it's usually -2. It's always -2 if it is combining with a metal. So the nickel was +3. Now you notice there are two charges of the nickel, but I told you by giving you this Roman numeral that the +3 was this charge. So we'd have a +3 there. We'd have a -2 here. So in order to make the charges balance, you have to have that by charges balance. In a chemical formula, you must have the total positive charge and the total negative charge equal to each other, just opposite in sign. So we need 2 atoms of nickel, and we need 3 atoms of sulfur. And the reason for that, of course, is 3 times 2 is 6, and 2 times 3 is 6. We want the positives and the negatives to be equal. Well, now we need to find the masses. So to do that, I'm going to put little arrows down here to show you where I'm going with this. So now for the nickel, if you flip back over to the periodic table, you'll notice that there are 2 numbers on this table besides the charges. There's an atomic number up here, and there is atomic mass here. It says rounded here because these numbers are the averages of the different isotopes of each element. Remember from first semester that isotopes mean atoms of the same element with different numbers of neutrons. So what we're going to do is use the number that's there, but I'm going to even round it further. So we're going to round to the nearest whole number. So if you look at nickel, you'll see that it's 58.69. The whole number place would be the ones place. So we're going to round to this place right here. So you look at the 8, and you have to decide whether to leave it as an 8 or round it up. You'll notice that the 8 is followed by a 6. And the convention that we're going to use, the rules for rounding are, if the number that we're rounding is followed by a number that's 5 or more, we're going to round it up. And if it's followed by a number that's 4 or less, you round it down. So if you look at 90, like zirconium here, be 91.2, so we just leave it at 91. But at niobium, if we're going to round it off to the nearest whole number, 92.9 is followed by a 9, so we'll round it up to 93. So back to nickel, it's 58.6. What do? Do we round it up or do we round it down? So we have to round it up because the 8 is followed by a 6, so we end up with 59. All right, so back over here, nickel's 59. Sulfur is easier to work with a little bit. Sulfur's over here, it's 32.07. Oh, it's followed by a 0, so we just leave it as 32. All right, so come back over here, sulfur's 32. Now, how many atoms of nickel are in our formula? 2, not 3. 3 is the charge. And after you've written the formula, you don't worry about the charges anymore. So we can just take them out of there. All right, so nickel's 2 atoms. Sulfur, there are 3 atoms. So we have to take this 59 and multiply it by 2. It is 118. Okay, and sulfur is 32. We have to multiply it by 3. So times 3, and we end up with 96. All right, so now the total weight of this compound is 118 plus 96. So we'd have a 14, 4, 1. That's a 2, and an 11, and carry another 1. So that'd be 10, 11, and carry another 1 over here, and that's 2. So 214 would be our total weight of the nickel 3 sulfide. All right. So now how many pieces are in that? Well, when chemists decided to use this formula weight as a standard, they decided we need to figure out how many pieces are in this many grams. And it turns out that you have the same number of pieces in the formula weight of anything. So 214 grams of nickel 3 sulfide contains this many pieces. See the 6.02 times 10 to the 23rd? So that's the second definition. A mole contains 6.02 times 10 to the 23rd. And that's pieces of anything, but a piece of nickel 3 sulfide we're going to call a formula unit. There's a reason for that. We'll talk more about that in a minute. Well, I'll tell you now. You can't call a piece of nickel 3 sulfide a molecule because it doesn't share electrons. It's an ionically bonded thing. Electrons are transferred from the nickel to the sulfur. So we call the simplest piece of that a formula unit. Just one Ni2S3 is a formula unit. And there are this many of these formula units in 214 grams. Take a quick look at another chemical, like maybe let's just do something you're familiar with, like water. Water, if you add up the weights, it'd be 1, the weight of hydrogen. You come over here. Let's see here if I can get back over to the table. Oops. So look at hydrogen. Its weight is 1, and oxygen's weight is 16. So back to calculating its weight. Since there's 2 atoms of hydrogen, you have to take the 1 and multiply it by 2. So 1 times 2. And oxygen is 16, but there's only 1 atom of oxygen in this formula, so it's just times 1. All right, so 2 plus 16 gives us 18, and that's the weight. So 18 grams of H2O contains that same number of pieces, 6.02 times 10 to the 23rd. But since water is made of all nonmetals, hydrogen is a nonmetal, oxygen is a nonmetal, then the piece of water is called a molecule. All right, so that's how many molecules there are in a mole. That number never changes. It's always the same. So if I had, skip over this for a minute, come down here. If I had a mole of eggs, it'd be 6.02 times 10 to the 23rd, eggs. It's just a number of things. If eggs all had the same exact weight, so if I knew that each egg weighed 2 pounds, then I could count eggs by weighing the eggs. Okay, so a mole, you see, is kind of like a dozen. So if you have a dozen eggs, it's 12 eggs. So a mole is just a number of things. All right. Okay, the third definition of a mole only applies to gases. So gases change with temperature and pressure. Therefore, we have to qualify our definition. It's 22.4 liters of any gas if the temperature is what we call standard and the pressure is what we call standard. And standard temperature would be 0 degrees C, standard pressure is 1 atmosphere. Right now, all the problems we do, we're going to do at standard conditions, so we're just going to pretend that we're always at standard conditions. So therefore, 1 mole of any gas is always going to be 22.4 liters. All right, so quick summary. There are 3 definitions of a mole. A mole is a number of things. this many. A mole is the gram formula weight, and to get that you just add up the weights off the periodic table. Or if it's a gas, a mole is 22.4 liters. So these definitions apply to all things. So if you have these two, if you have a solid, it'll only be these two definitions, but if you have a gas, all three definitions apply. If you have a liquid, these two definitions apply. If you have a gas, again, all three. So that's what a mole is. The most practical definition is the weight definition, and that's the one that we will use the most. All right, I'm going to stop this video, save it, and then I'll make another one going over some examples that we've done in class. And then we'll take a look at how to do some conversion problems between particles and moles and liters and grams. All right, that's the end of this one.